Hello everyone, I am Mohaiminul. I will present our paper Efficient Movie Scene Detection Using State Space Transformers. We propose an efficient model for movie scene detection called transformer. Given a long movie video, our model can divide the video into scenes. Here, scene represent high-level semantic units of a movie. For example, here we show three scenes from the movie Godfather. Generally, movies are composed of well-defined scenes, and understanding scene is essential toward high-level movie understanding. Moreover, scene detection can be applied to other applications such as content-driven video search and preview generation. Most standard video recognition tasks such as action recognition and object detection require a short-range analysis of video clips lasting only 5 to 10 seconds. However, movie scene detection require both short-range and long-range understanding where videos may last for several minutes. For instance, to successfully recognize the scenes in this figure, we need to identify the visual concepts in each frame such as characters, objects, and backgrounds, while also reasoning about complex temporal events and activities. Most existing works operate on pre-extracted CNN features or use a small transformer network on top of a CNN encoder. However, we know convolution are inherently built for short-range analysis and are limited by its small receptive fields. Unlike CNN, transformers are very effective at capturing long-range global properties. However, transformer model has a quadratic cost associated with the self-attention operation. Therefore, applying transformer for long-range videos is too costly. For example, if we have a video of 100 frames and we divide each frames into 14 into 14 batches, applying a standard self-attention layer would require 384 million pairwise comparison, which is computationally too costly even for modern GPU machines. Recently, a new type of sequence model has been proposed called structured state space models. S4 model can be defined by these two simple equations. Here, U is the input sequence, X is a latent state, and Y is the output. Unlike self-attention, S4 has a linear memory and computation cost. Here, L is the sequence length, B is the batch size, and H is the hidden dimension. Moreover, gated S4 models further improves the efficiency through a gating mechanism. Before going into the details of our model, let's have a look at the hierarchical structure of our input video. First, multiple consecutive frames captured from the same camera position depict a shot. Next, multiple neighboring shots constitute a scene. Finally, a movie is composed of a collection of scenes. Unlike scenes, shots can be easily detected by low-level visual cues. Our model takes a sequence of frames divided into automatically detected shots as input. First, we divide each frame into non-overlapping patches and pass through a linear projection layer. Afterwards, we feed these patch level tokens through our transformer model, which consists of B state space self-attention blocks. Finally, the CLS token of all shots are passed through two linear layers, the boundary prediction head and the contrastive head. Each S4A block is composed of two modules, self-attention based intra-shot module and state space based inter-shot module. First, patch level token are passed through the intra-shot module to capture short-range interaction among frames in the same shot. Intra-shot module first applies a MLP and then a self-attention layer. Layer normalization and residual connection is also used. Then they are passed through the inter-shot module that aggregates long-range temporal cues from different shots. Each inter-shot module uses a MLP and a gated S4 layer. We experiment on three movie scene detection data sets. First, MovieNet is a large-scale dataset containing 1100 movies with 1.6 million shots. Second, BBC contains 11 episodes from the BBC TV series Planet Earth. And third, OVSD contains 21 short films with an average duration of 30 minutes. We implement three more baselines apart from our main model. First, we implement a self-attention based transformer baseline where we replace the gated S4 layers with self-attention layers. Then our timesformer baseline replaces the gated S4 layers with divided space-time attention layers. Finally, vanilla S4 layers uses vanilla S4 instead of gated S4 layers. Here we show the main results on the MovieNet dataset. We can see that our model achieves the state-of-the-art performance in all metrics. Transformer is also 2.5 times faster and 3 times memory efficient than prior based method BASSL. Moreover, transformer is 2 times faster and 3 times more memory efficient than self-attention based baseline while achieving better performance than all other baselines. Here we show the results on BBC and OVSD. We can see that transformer outputs the prior based method BASSL by a large margin on both of these datasets. We perform ablation studies by removing either intra-shot or inter-shot module from our model. We can see that removing any module drops the performance significantly, which shows that these models are complementary. We also ablate the position of S4 layers and different types of S4 variants. We found that gated S4 layers at every S4A blocks yields the best performance. Moreover, we study the temporal extent of the input video of our model. Here we show the performance as a function of number of input shots. We can see that self-attention baseline performs better at shorter videos, where our model achieves much better performance on longer videos. Finally, we experiment with other tasks including long-form movie clip classification and long-range procedural activity classification. First, Transformer achieves the best performance in 5 out of 7 long movie clip classification tasks in the LVU benchmark. Then we can see that it performs based on the breakfast and second based on the coin procedural activity datasets while using significantly less pre-training data. That is all. Thank you everyone.